Can start after, let's say, 20 seconds. Hello everyone, welcome to the first lecture of Unit 3. During the next hour, I'll introduce the concept of synthesis. I'll start with the very basic. What is synthesis? What does the process do? What does it need? And most importantly, where does the process of synthesis fits in the ASIC design flow? We would also look at the design compiler family from Synopsys, which I believe all of you would be using in your project works and assignments. And further, when you go into the industry, Synopsys design compiler is in fact the most popular tool of choice for synthesis. There are other tools also like Cadence RTL compiler. There's Magma, but we'll focus our all the commands we discuss, all the scripts we see will be focused to Synopsys design compiler. However, it should not be a major problem in switching to a different tool if you want to, if the need arises, because the concepts remain same. Only few commands are different from one tool to other. Otherwise, everything else remains same. So, what is synthesis? Synthesis, by definition, means combining pre-existing elements to form something new. Or in other words, you can also say that synthesis is nothing but conversion of an idea into implementation. We introduce one more thing called logic synthesis. Again, logic synthesis is combining primitive logic functions to form a design netlist that meets a functional and design goal. So here on the left hand side we see a jigsaw puzzle which is jumbled up. Each of the component is labeled as TP. TP means a technology primitive. This could either be a RTL written in Verilog or VHDL, and then we want that Verilog or VHDL to be converted into a gate level netlist, which would again be sent to fabrication. And this process of conversion is called synthesis. Obviously, it should meet some of the goals. For example, let's say we are working on a processor from Intel. Now that processor, each processor from any company will have some frequency goal. Let's say the goal is it should meet 1 GHz. So that is our goal. So whatever design we do, whatever technology node we choose, we have to make sure that the processor meets the criteria of 1 GHz frequency. So that is an example of a goal. The output is netlist plus a lot of other files which go to physical design tools, and then layout is done and they are sent to foundry. The concept of automated design is theoretically it is possible to convert any digital function to a logic circuit. This is what is done by the synthesis tool. It automatically synthesizes circuit from function description. For example, on the left hand side you have a logic function that is equal to A or B and C or D and E. Now this statement on the left hand side is written into a high level language. It could be Verilog or VHDL. So the tool will read this and it will convert this to something represented by the right hand side, which is a logic circuit. This is a very simplistic explanation of the process. Now we are assuming some things here. One thing we are assuming is that the standard cells, that is the cells, the logics, like in the previous example, the OR gates, the 2 OR gates and the 3 input NAND gate, we are assuming their existence. So if primitive standard cells are previously designed, we are assuming that these cells are previously designed. That is, we have a library which contains all these cells, and we have the functional description of these cells. We have the timing specifications of these cells. We have the layout of these cells. That means everything is already designed. We could build a large number of various digital circuits using these parts. So the group of primitive cells which are used to build larger circuits is called standard cell library. Now, building a standard cell library is a completely independent subject on its own. It involves a lot of size analysis, layouts, and all that. So during this course and during your project work and assignment, we will be assuming that we have a library of standard cells available with us, and we will simply use that library to create circuits of choice for our application. In the next lecture, we would actually spend a lot of time on understanding how the standard cell library data is represented, what files do we need, what do those files contain. So we will see a lot of that, but we will assume that everything is available for us. We just have to start from the design. Now, Synopsys has a library available for university students. It's a 90 nanometer generic library, which can be used for project works and assignments. Now, why synthesis? Why can't we start with? Why can't we hook the let's say assume you have to design a decoder. Let's say 3 to 8 decoder, what we saw in an example of that. And now there can be two approaches. First approach can be that I know what a decoder looks like, what the logic circuit looks like. I can draw it on paper. Then I can go to the library and choose the cells, the appropriate cells, hook them up, form the netlist myself, and then proceed through the physical design part. Second approach, which is a high level approach, what I would do, I would write an HDL, which is I would write an HDL in Verilog. Let's say in Verilog, I write something like this for the decoder. I use synthesis to convert this into a netlist, into a gate level netlist, and then again proceed for physical design. This is possible only for very small designs or very specific designs or some very special circuits where you do not want the regular digital design synthesis code. You will find that not useful. But otherwise, for all big designs, huge designs, big chips, obviously drawing circuit by hand is not at all possible. Plus, the tools nowadays are very sophisticated in terms of that they can choose what cell would suit best for, let's say, different type of code. For, let's say you want a lower area, so it would choose a different cell when compared to when you want a faster circuit. And the complexity keeps on increasing as you go one level down. So an HDL will have, let's say for a full chip, an HDL will have a few hundred files with some thousands of lines of code. And then when it goes through gate level, it expands into 1 million gates which are hooked up together. Again, when it goes to, now since gate level database is not the one that is manufactured, we convert this gate level database into a transistor level schematic using physical design tools. And then this again, each gate will have let's say n number of cells. We saw that a 2 input NAND gate is comprised of 4 CMOS, or 2 NMOS plus 2 PMOS. That means 4 transistors. So similarly, let's say you have a 1 million design gate level netlist. It will translate easily into a 5 to 6 million transistor count. Again, this transistor count is then converted into polygons, which is nothing but layout. So layout, we also call them as polygons because ultimately they are just a bunch of rectangles, squares, different type of polygons which represent different layers of the chip. So some polygons will represent the metal layer, some will represent the poly layer, and so on. So as we go down the hierarchy, so the number of elements increases exponentially, the complexity also increases, and dealing with a higher complex, very complex design in the sense of, let's say, if you are working on gate level netlist, that will take more effort, time, and cost when compared to working on an HDL. We will see that the differences that Is there any need when we need to work on a gate level network? Yes, there is a need when sometimes we need to directly work on gate level network. But most of the time, for our course, purpose of our course, we'll start with an HDL. Almost always we'll start with a Verilog or VHDL description of a design and then proceed for synthesis. I would also assume that almost all of you should be familiar with Verilog. We will, whatever code we see here will be Verilog because it is the most popular language of choice right now presently. There are VHDL users also, but I would restrict my slides or codes to Verilog. So if somebody is not familiar with Verilog, I would suggest that they read up Verilog. It's not a to start with it. You could start in a 2 or 3 days. You could read about it and start coding. It's not a big problem. And then you come back to this lecture so that you can understand it better. Not this lecture in particular, but all the coming lectures which discuss synthesis. Now, logic synthesis is divided into 3 parts. The first part is called translation, second part is called mapping, and the last part is called optimizing. The first part, the translation, is a name given to the process of converting the HDL description into something called a GTEC netlist. So GTEC is a term specific to Synopsys. GTEC means generic Boolean. So now let's say so the hardware description language, the Verilog code on the left hand side, this code here would be pricing of higher level language constructs, if else, case statements, always blocks, and so on. So this HDL here, the art here, is actually technology independent. That means it does not matter what technology node we are targeting for. The RTL does not need to represent that. When I talk about technology node, I mean, let's say we are targeting either 90 nanometer or 65 nanometer, where the nanometer length is the transistor channel length. So each technology node, for example, a 90 nanometer technology node, corresponds to the manufacturing process where the channel length of NMOS and PMOS is 90 nanometer. So when we go for deciding a chip, then we have to choose a technology node. But when we write the RTL, when we write a high level description language, the design is technology independent. When it goes through translation, it gets converted into something called GTEC netlist, the generic Boolean netlist, and this netlist also is technology independent. That means till the process of translation, till this generic Boolean, we are not concerned about what technology we are going to get our design manufactured in. Right now we are only concerned about the logic that is represented by the RTL. The second part of the process is mapping. Mapping is the process where design compiler will map the GTEC Boolean into the gates available in your library. Here is where the technology comes in. So let's say I am targeting my product for a 90 nanometer technology. I would have a 90 nanometer standard cell library with me. Now that standard cell library will contain a lot of cells, different types of ANDs or NAND or inverters, couplers, and so on. And now this generic Boolean will be mapped into this gate level netlist. And the last part, which is the optimization, will make sure that all the goals that we have specified in terms of performance, area, and power are met. Now let's say the same design I have manufactured in 90 nanometer. Now I want to go to 65 nanometer. The first part, that is translation, will remain same. It won't change because the generic Boolean is not changing. It is same irrespective of technology. It is same. It is simply a collection of gates that design compiler. The gates that are available in design compiler, they are not linked to any technology. they are generic. So the first process will not change. The second process will change because the 65 nanometer library would be different from 90 nanometer library, and because the second part is changing, the mapping part is changing, the optimization will also change, because now although the goals might be same, but the underlying cells are different. So the optimization of that part would be optimization carried out by design compiler on a 65 nanometer design can be and will be different from the one in 90 nanometer. Now first we start with the functional description. It is written in a hardware description language, Verilog or VHDL, or we also call it RTL, to register transfer level. Most of the designs which you will practice hands-on will be synchronous. Synchronous means there will be a clock. All the handshake between different parts of the design will be based on a clock signal. The very big advantage of a synchronous design is the reliable behavior. This thing is very important. Simplifies timing verification. We will see that further in Unit 3 and Unit 4. What do we mean by this? It simplifies optimization algorithms. Again, this is again a derivative of this fact saying simplified timing verification. Optimal results. It is very easy to set goals for a synchronous design as compared to an asynchronous design. Asynchronous design is very difficult to verify and to meet timing. So it is recommended that whatever design problem we have, we try to solve it in the synchronous domain, and so that goal setting and optimization would be easier. Again, the way we code RTL, it affects the results. We will see that in another coming slide. How do we write better codes, and how do we make sure that this one very famous saying is that when we write RTL, we should think in terms of hardware, not in terms of software. That is, let's say we are writing a case statement, we should think that what that case statement will translate into after synthesis. What type of hardware will it consume? So a lot of the area of the design, the performance of the design, a lot depends on how do we write the code. So the process of translation now we see in detail. The process of translation will cover all these things. It will do SGL syntax and rule check. It will optimize SGL. We'll see few reports. How does it do that? It will map arithmetic functions. For example, let's say you are writing a plus b. You are writing c is equal to a plus b. So that plus looks very simple in Verilog, but that plus translates to an adder in hardware. That adder would be mapped to a GTEC adder, a generic Boolean adder. This is what is meant by arithmetic function mapping. Sequential function mapping. Whenever you have always block that represents a flip-flop or a latch, that particular register will be mapped to a generic flip-flop or a generic latch. Then there will be combination function mapping, that is mapping of and ORs. All this mapping is still done at generic Boolean stage, at a GTEC stage. The second and third parts of the process are combined together. We call it mapping or optimization. It maps Boolean functions to technology specific primitive functions. It modifies mapping to meet design goals. So this part here is actually the optimization part. So when it says it modifies mapping, so the first pass synthesis will just map the generic Boolean. It will map it to a target technology, and then in the next pass it will start optimizing. It will start looking at your clock frequency. It will start looking at the timing, which is given in the library files. It will start looking at the area of the design. It will start optimizing the design for all these 4 parameters. So these 4 parameters are the key, and they are in fact in order of priority. So the design rules come first. We look into detail what design rules mean. Just a hint, it means that the gates, the logic circuit, the individual gates, let's say ANDs and ORs, NANDs and ORs, they are not driving any load which is beyond their capability. This should be met first up. If design rules are not met, the timing is not reliable. So for timing to be reliable, design rules have to be met first up. So this is the highest priority. This goes number 1. Timing goes number 2, because if timing is not met, it is not guaranteed that design will function correctly. Area goes number 3. That's the almost the second last. Since we have to first make sure that the circuit is accurate and is accurately timed, then only we should talk about area. Third comes area, and again last comes power, but power can be given higher priority in some cases. The priorities of these are dynamic, but this is the general rule: design rules, timing, area, and power. The process of optimization is constraint driven. So there are few statements written here: create clock, set input delay, set output delay, set max area. Don't fret too much about it. Just the first 3 lines represent the timing goal. The last line, max area 0, represents the area goal. It just tells the tool that just work hardest. I mean, saying set max area 0 will actually not result into a 0 area. It's just a method of telling the tool that do your best job. So what the tool will do, it will try and meet timing, and for a design represented by the top 3 lines, and for that, let's say there are n number of configurations, which all of, let's say there are 5 configurations, 5 types of different gate level netlists, all of them meeting the first 3 statements. Among these 5, the tool will choose the one which has lowest area. That is meant by set max area 0. So now we see a very nice graph here. On the x-axis is the delay, or you could also call it the performance of the design. On the y-axis we have area. Now, if you go from left to right, that is the delay is increasing, that is the performance is going down, and the area is also going down. If we come to the, if we go see the lower area, the small area, this quadrant here, this is. So for a smaller area, the delay, for the larger area, the delay will be shorter. So if so, these two are fighting each other. The area and the delay always fight each other. There's one more angle to it called power, but let's simplify and see area and delay first. Now, if you want to reduce area, what you would do is you would add more sequencing. That is, let's say you have a decoder kind of example. The more parallel paths you have, the larger will be your area, and it will be faster. But if you increase the number of stages, the area will be less, but the circuit will be slower. It again, even if we talk about the cell design, the cells which are faster and have better drive strength are always bigger in area, because again their W/L ratio will be high. They'll probably have inbuilt inverter or buffer stages. So these two things, area and delay, are always fighting each other. And the process of optimization is entirely dependent on the constraint feature. The set of 4 statements here, these 4 statements are what we call constraints. Same function can be represented by different circuits. We see that you could have a NAND NOR based circuit. You could always have an AND OR based circuit. Let's say in a MUX based design, you could actually use a simple MUX, or you could implement a MUX using AND gates and OR gates. So, and different circuits will have different physical parameters. The tool will choose what to take based on our constraints. So let's say you have a function y is equal to a and b and c and d. The variant one on the left hand side is a circuit where the first stage uses 2 input AND gates, the second stage uses a 3 input NAND gate, a 3 input AND gate. On the right hand side you have a 4 input AND gate and there is one 2 input NAND gate. The power number and the area numbers are just some random numbers here. They do not represent actual. They just tell that what is higher and what is lower in power and area. So obviously the 4 input AND gate, if you actually go and draw the CMOS circuit of a 4 input AND gate, you will see that it's a pretty large circuit. Correspondingly, the 2 input and the 3 inputs are lower in area. So we see that the variant 2 area is higher, but power is lower, or let's say comparable to variant 1. So and again, if we see, there's one more important thing is that if we see the delay from E to Y in variant 2, the delay from E to Y, let me change the color here. The delay from E to Y just crosses one AND gate, but delay from, assuming this is E, the delay from E to Y here crosses 2 AND gates, or you could also say E is here, again it will be crossed. But so the delay from E to Y would be different in variant 1 and variant 2. Now the constraint that we give on E will also determine what variant will be picked up. So that the table here shows that it shows the representative power and area numbers for cells. So obviously a 2 input AND gate will have the lowest power and the lowest area. A 3 input will have more power and more area when compared to the 2 input. Again, as we keep increasing the number of inputs in a gate, the power and area keeps on increasing. It does not mean that gates which have a number of inputs higher than 2 or 3 are undesirable. That will again depend on our delay requirements. So obviously, let's say a 3 input AND gate, the delay from from input 1 to output, from input 2 to output, from input 3 to output, all will be similar in nature. Whereas let's say if you try and use always a 2 input AND gate or 2 input gates, you will see that the delay keeps on increasing, since you will be adding more stages to your combination logic. So this is why we say that the delay and area are always fighting each other. So the more number of stages you have in a combinational path, it will be slower, but it will have lower area. If you decrease number of stages and increase the parallelism, you will have more area but faster circuit. So let's see what optimization trade-offs are. So the circuit, as we saw, the circuit design goals are, the first goal is obvious, that is it should meet design rules. Then comes timing, so we should have small delays, that's our goal. Power, we should have lower power consumption and smaller area. Now you cannot meet all three if all three are very aggressive. So circuit design is a trade-off of timing, area and power. Optimal design, when we say optimal design, it means that it meets all our goals, is found as a result of synthesis based on the priority set by designer. So let's say there is a CPU, let's say there is an 8-bit CPU or 8-bit MIPS microprocessor, design of that. Now let's say I synthesize it for a 400 MHz target, and then again synthesize it for a 600 MHz target. What do you think will have more area? Obviously the 600 MHz will have more area, because I am asking the tool to give me more performance, but there will be some cost, and the cost is area and obviously the power. So 600 MHz microprocessor netlist will have more area and more power when compared to a 400 MHz design. This is what is meant by the priority set by designer. For example, when the delays are small, the power consumption is high, and vice versa. Circuit variant is chosen on the basis of the importance of one parameter against the other. So in fact, the most complex part of synthesis is actually setting the goals. You have the goals in mind, but then we have to translate those goals into a number of commands given to the synthesis tool. This is the most important and most difficult part of synthesis. How to make sure that whatever goals we have on paper are given correctly to the tool. So the goals, the design goals, timing, area, power are defined by something called constraints. So constraints are the set of rules that will set limits on circuit parameters and it will set priorities. So during synthesis process, every time there is a choice, every time the tool has a choice between several circuit variants, the one meeting your constraints is always chosen. So you could say, in other words, that synthesis is nothing but an optimization problem. So if we go back to most of you would have studied the course of optimization, and in optimization there's a very famous and a very interesting problem called a traveling salesman problem. So if you haven't read about it, please read about it. It's a very interesting concept. It tells that it tries to solve a problem of a traveling salesman. He has to travel, let's say, through 10 cities. So now the goal can be multifold. One could be a traveling cost, other could be a traveling time. Now let's say we assign that, okay, if he goes from A to B, the cost is, let's say, X. If he goes from B to C, the cost is, let's say, Y, and so on. This is a problem. Now there's an algorithm which tends to solve this traveling salesman problem and optimizes the total cost. Exactly same thing happens in synthesis. The constraints set a goal and the tool will try to optimize the circuit based on the constraints. So it's nothing but an optimization problem, and every optimization problem depends on the goals we give. Next we see something called environment attributes. Environment parameters and net attributes affect circuit operation. Now we saw in synthesis we have been talking about picking up gates. We are not talking about how they are connected together. That means what are the parameters of the interconnect, the copper interconnect connected together. Please note the interconnect information is only estimated during synthesis. It is never accurate because circuit the accurate information, interconnect information, only comes after physical design, after the layout is done. So in the process of synthesis we do not have the layout information obviously. So any interconnect information we provide is based on some estimates. We will see what those estimates are. The synthesis steps need to account for such estimates for correct results. So we should provide this data. One thing which we know for sure will be environmental parameters. That is, we know that a design should work at a particular voltage, temperature, and some process variations. The net attributes, the parasitic resistance and capacitance, are at best estimates at this point, at the point of synthesis, but we should provide something. It should not be taken as zero. It will be inaccurate. So the environment parameters here, very interesting concept. Let's see. So this figure here tells what goes as input to synthesis and what comes as output. Logic synthesis tool, we give it the RTL code. Okay, let's go in order in which we will actually do the process. So the first thing that we need to set up, we need to decide is this: what technology are we targeting, and then provide that particular cell library to synthesis. Second, we should know what are the environment attributes, that is, what are the operating conditions we are targeting. Are we targeting a 1.0 volt? Are we targeting 1.2 volt? This will affect synthesis, and actually this will affect this also, because environment attributes, that is voltage, process, and temperature, actually also determine the cell library. Usually you have because the timing of the standard cell let's say timing of an AND gate will change depending on what is the voltage, what process are we talking about, and what is the temperature. So by fixing the environment attribute, we also fix the cell library, and in turn we provide the library information and the operating condition to the tool. Then we go on and give the tool our RTL code, and then we define we give this, and then we give this, we give the constraints. These are the inputs. What comes out is this. What comes out is a gate level netlist in Verilog or VSDL. Let's say Verilog. So the gate level netlist would be in Verilog, and then this gate level netlist goes to the physical design tool, the physical synthesis tool, where actually the netlist, the gates are laid out, the wires are, the actual wires are drawn, routing takes place, and so many things happen. As far as this course is concerned, we will not be looking at this. Our job is to make sure that we get a correct gate level netlist out from the logic synthesis tool. So we would be looking at cell library in the next lecture. We will go into details of how a cell library looks like, what does it contain. We will see how to specify environment attributes. We will see examples of this course does not teach Verilog, it assumes that you know Verilog, but we will go through the good practices of Verilog coding, of RTL coding, what type of code results into what type of hardware. We look a lot into constraints. This is the most important part, and we look very heavily. We invest very heavily into this. We'll see how to specify this, and obviously we'll see the commands related to all of these processes. Now let's see where does design compiler fit in an ASIC design flow. So the ASIC design flow is something like this. Obviously we start with an architecture. The architecture will tell the scope and the problem description. For example, let's say we want to design an 8-bit RISC processor. This is the design. This is the problem statement. Now we would go and finalize the architecture. What type of registers will it contain? What frequency are we targeting? That will in turn decide what technology node we should choose, and so on. Then we will start coding. So we'll start writing the microprocessor code in Verilog, so which is the SJ description. Then now since we have, let's go back to the previous slide. We have this RTL code, we have the cell library. Since we chose the technology, we have environment attribute. We'll go on, and there's one more process which comes, which is not represented here, is the functional verification, simulation. That is, we have to first make sure that whatever we have written in Verilog actually conforms to the functionality that we defined in our architecture. So this is again a separate, very big field of which is called verification. That is, you make sure by using some test stimulus that the RTL code, the Verilog code actually performs according to the functional expectations. So once we have made sure that the RTL actually is verified 100%, we go to synthesis. You could also use synthesis for design exploration. Obviously, you do not need it to be passing 100% verification. You could also do that. Many people do that. So we go to design compiler. In design compiler, there is a tool called SDL compiler, which actually reads the Verilog and does few things. It checks syntax and all. Then it goes to GTech. It does timing optimization, data path optimization, power optimization. So design compiler is nothing but a bouquet of tools. So inside design compiler, you have SDL compiler, you have power compiler for power optimization, area optimization. Then if you want to add some DFT features, there's a DFT compiler, and timing closure, and so on. So the loop here, this loop actually shows that this process is iterative, in the sense that if you do not meet your power or timing or area goals, you go back. You either go back to RTL, or you go back to your of goals. You reset, you change the goals, you modify them, and you make sure that this whole process is passing. The input to this process is constraints. The file format is called SDC. You'll see this. Designware library, we will see what designware means. Technology library, symbol library, and so on. Don't worry too much about def for now. So the output is optimized netlist. This optimized netlist goes to some physical design tool. One example is IC compiler, something like this. It goes to place and route. And now we have to also make sure that the netlist here, optimized netlist here, is equivalent in functionality to the RTL layer. These two are equivalent. We have to make sure. This does not mean, please note, this does not mean that the tool here, the Synopsys design compiler tool here, has some problem. It can mean that whatever RTL, whatever SDL description we wrote is not actually good enough to produce a good netlist. There can be many reasons why these two are not equal. These two are not equal. There can be many reasons why these two are not equal. But we will see in the process of synthesis that what could those reasons be. But we have to make sure that these two are equivalent. The process is called formal verification. Formality, we'll look a bit into this during this course. We'll see why this is called formal and what is the difference between formal and stimulus based. So just note that you could now somebody could ask that during the verification of my RTL code, I have a test, I have a stimulus. Now I can use the same stimulus on a netlist and make sure that the functionality is correct. Yes, you can do it, but formal verification is a much more sophisticated and much more accurate way of doing it. Please hold this thought for a while. Now the high level, we go a bit deep into the flowchart, goes a bit deep into the high level design flow. So you have design data preparation, which includes SDL coding, constraint generation, library development. We will not be looking into library development. We are assuming that library is already provided to us. Then we go into goal specification and function simulation, what I was talking about. There is a tool called DC Explorer which will help you in doing some design exploration. We will not go into that. We have to make sure that the design meets it is within 10% of time inputs, then that's an arbitrary requirement. Then we go to design compiler. The first process, what it tells here, is actually the design exploration stage. That is, many times when you are starting a fresh design, you are not even sure what goals you should set. So this process actually helps us in doing that. It helps us in using the DC Explorer. DC Explorer, what it does is it will do a very basic floor planning, because any feedback on how the design will look after place and route needs to have some floor plan information. So the design explorer will DC Explorer, it helps you in floor planning the design. But we are not going into that. Just make a note that the process here, the first half, will help us in setting the goal. Now we have the SDL design ready, we have the goals ready. Now we go to design compiler, and again the flowchart tells us that if we do not meet our goals either before physical design or after physical design, we have to go back to design compiler and either modify our goals or modify our design, one of these. Now let's look at the design compiler family. The first and foremost tool we are looking at is DC Expert. So you don't have to actually start up different tools. So when you start design compiler, we call it DC shell. This is not a single tool, it has a bunch of tools inside it. So all commands will work there for all the tools. So you don't have to worry about invoking different tools for different applications. Obviously, for each tool has something needs a license. For example, DC Expert needs a license. We'll see there's one more tool called DC Extra. So each feature, I'll call them as feature. Each feature needs a separate license from Synopsys. So depending on what licenses do you have available with you, those features will be available in your design compiler, in your DC shell. So DC Expert is a basic synthesis compiler. It provides optimization for area timing power. using wire load models for delay estimation. Wire load models estimate the interconnect delay. We'll see what they look like. So what capabilities this tool has? It provides hierarchical compile, that is top down or bottom up. We'll see in detail what does that mean. It gives full and incremental compile techniques. It does sequential optimization for complex flip flops and lattices. We saw time borrowing, so it is able to do that for latch bit designs. Timing analysis, any synthesis tool should be able to do basic timing analysis to make sure the timing is meeting. We'll see a lot more of that. It has command line interface and graphical user interface. First up, when we start any tool, we are tempted by the graphical user interface. But for tools like design compiler and time, you would be heavily using the text-based interface. I personally favor text-based interface because it gives a lot of reporting capabilities. The graphical user interface is only useful to see the circuit, but for a bigger design, you actually don't want to go into that until there is some very exceptional and big problem, because it will contain multi-million gates and you don't know where to start. So that's why I prefer text-based, the command line interface. It gives a lot of reporting capability. The advanced, so DC Expert is the basic synthesis feature. The advanced is DC Ultra. What is being used into industry, we use DC Ultra. It is much more advanced version of DC Expert. It does, apart from what DC Expert does, it does an advanced arithmetic optimization, advanced delay optimization. It helps in critical path resynthesis, register retiming, which is a very important feature. It helps us doing that. It does advanced. It has capabilities for advanced timing analysis. So you see a lot of advanced here. So it is just an advanced version of DC Expert. It is also capable of running into for big designs. It supports multi-core execution for faster runtime, which is very important for big designs. Rest of the things are same as DC Expert. But for the scope of this project, actually DC Expert should be sufficient, unless and until you are going for very high speed design or something like that. DC Expert should be sufficient. And there is a graphical user interface for this is called Design Vision. Again, it's a separate feature, not a separate tool. So it provides analysis, viewing and analyzing designs at GTech level. So it provides menu, dialog boxes, drop down menus, and so on. But I would recommend starting with and sticking with the text-based interface, that is the command line interface. It will be much more intuitive than the graphical user interface. As you start practicing onto this, you will see the reason why. There's a feature called SDL compiler. So SDL compiler, it translates your Verilog and VHDL into GTech. So again, you have this SDL compiler is very much like a Verilog compiler, what you might be using in your other course. So for example, NC Verilog, this SDL compiler has a lot of those features. That's what it does. Now your Verilog code will not be same. So not 100% of Verilog is not synthesizable. There are constructs which do not have any hardware equivalent. For example, in Verilog, many times we want to delay something, we write hash and a number. Let's say hash 5. Hash 5 A is equal to B. That is B is being assigned to A after 5 units of delay. Now this particular delay unit, that is hash 5, has nothing equivalent to in hardware. That is, yes, we have hardware, we have buffers and inverters which we provide, which will give some amount of delay. But saying hash 5 will not result into some hardware. That is, the synthesis tool will simply ignore hash 5. So this SDL compiler helps us in analyzing if our RTL code is actually synthesizable. It will give out warnings, it will give out errors if you have cases like this. So you could use this SDL compiler into correcting your design. There's a family of components called DesignWare. Now, if you go back and remember that, recall that The process of translation converts the RTL into a GTEC netlist, into a generic Boolean netlist. So, designer library is a collection of reusable circuit design building blocks which are tightly integrated into synopsis synthesis environment. So, let's say if you have the license for this feature available, and let's say you write A plus B in your RTL code. Now, this plus, now assume the A and B to be, let's say, 8-bit. Now, what we are doing here is we are doing an 8-bit addition. That adder will not be a simple adder. Now, this designer library contains a lot of adders, ripple adder, you have carry look ahead, you have carry save, and so on. So, it implements all the adder architectures, and you could use them or tell the tool by simply writing A plus B, and also telling, so if you write A plus B and simply synthesize, if your design requirements are not too aggressive, if you don't need a very fast adder, it will pick up a ripple adder to implement it by itself. Now you could tell the tool, you could tell design compiler that do not use ripple adder, it's slow, use some other adder architecture, so it will do that. So a designer library is a collection of all such adder multipliers and so on. There are a lot of components there. So it contains a lot of components which will help you in designing complex circuits, and it is very tightly integrated into synopsis synthesis environment. So during synthesis, design compiler will select the right component with the best speed and area optimization from the design library. Many times you do not need to specify this in your RTL code, but I have seen people they are very particular that okay, for example, I would want that in all the cases my RTL code, the multiplier I use should be a boost multiplier. So I can actually specify in my RTL that for a multiplication operation I can say that okay, use GW underscore mult 01. Let's say this is the name of a designer component. I could directly instantiate this in my Verilog, and DC and synopsis design compiler will pick it up and synthesize it. So this is all. In the next lecture, so what we saw. Let's review a bit. So we saw what the process of synthesis is. It combines the process of synthesis can be broken into 3 parts: translation, mapping, and optimization. The translation is simply conversion of your RTL code into a generic Boolean netlist. The process of mapping and optimization actually converts that Boolean netlist into a specific technology library netlist and further optimizes based on the goals we provide. We saw that the goals we provide are timing, area, and power, assuming all the design rules are met in that order of priority. So we will see next lecture we look into the library, the standard cell libraries, what types of standard cells are there, how is timing and area information represented, how to read that, it is very, very important. Then we'll begin with the RTL code. We'll see the good practices of RTL coding for synthesis. We'll see the process of synthesis. We'll spend a lot more time on writing the constraints, writing how to mention the clause, how to set timing goals, how to set area goals, and so on. Thank you.